Hello dear students, let's see how to construct PDA for the given grammar. Now just check that the grammar given over here is of course CFG. This is a context free grammar, but it is in the form of GNF, Gray Batch Norm Form. Remember, Gray Batch Norm Form is nothing but a CFG, but with a rule that right hand side of the production should be starting with a terminal followed by any number of non-terminals. Just one terminal in the beginning followed by only non-terminal, 0 or more non-terminals. So you can see first production, second production, both are in GNF because the right hand side is beginning with a terminal followed by a non-terminal. Here also in the first production, right hand side begins with a terminal, correct, followed by list of non-terminals. Third production is also in the form of GNF because in GNF the right hand side of the production must begin with a terminal, correct, followed by 0 or more non-terminals. So there are no non-terminals here, that's fine. And even the fourth production is in GNF. Now the fun part about this is that if we are given a GNF, all the productions are in gray batch normal form, then the PDA, pushdown automata, can be easily constructed. It means it can be constructed automatically. What am I talking about? Look, all the previous problems that we solved on PDA, where actually those PDAs were constructed by hand. By hand, what I mean is that we thought about what should be the next transition or configuration. Should we change the state or should we remain in the same state? All this thinking was done by the designer of the PDA, that is we. But the good part about GNF is that if GNF is given, you don't have to think about transitions. You don't have to think about states. You don't have to think about stack symbols. Everything is automatically done, created. Just follow these steps. How do you create a PDA? Before I show you the steps, note that the PDA that we will get, will be non-deterministic pushdown automata. Come again. If we are given a GNF and we are constructing PDA using GNF, then we get NPDA. Remember this, I'll come to this point when this topic ends. But first of all, what does a PDA contain? PDA contains set of states like Q0, Q1, Q2 and so on. Set of input symbols, like in this problem the input symbol is A, C and D. That is, input symbol is nothing but terminals in the grammar. After that, we have something called stack symbols, which we are going to push or pop from the stack. Now, recall in the previous problems when we constructed PDA by hand, we took stack symbols like Z0. Z0 was the initial stack symbol. We took stack symbols like X, Y, and so on. Now here the stack symbols are going to be non-terminals of your GNF. Which non-terminals are there in the given GNF? NTs. Non-terminals are S, A, B. That's it. These will be the stack symbols. Just check how stack symbols can be easily found out from the given grammar. That means we are going to push or we are going to pop these stack symbols SAB. What else do you have? Very importantly, the transition function delta. That is, given a state, given an input symbol and given the top of the stack, what should be the action taken? Nice part about this delta, is that this delta will be automatically created using these above productions. We will see that. Further, there was initial stack symbol. Recall, what does stack contain initially? We said that the initial stack symbol will be Z0 in our earlier examples. Now here in this, if GNF is given, then the initial stack symbol will be the start symbol of the grammar. And finally, set of final states. What will be the final states? Now the fun starts here. See, in all our previous PDAs, there was a final state. We had two types of PDAs. Recall, PDA by final state and PDA by empty store. Now the PDA that we are going to construct is not going to have any final state. So which type of PDA it will be? Yes, which type of PDA? PDA by empty store. Let's elaborate. Q is set of states. Now in this construction, there will be only one state in the PDA. What? Yes, only Q0. This will be the initial state and this will be the only state in the PDA. You may ask, what about final state? I already told that there is no final state in this PDA. I have removed that capital F. Okay, what about sigma? Input symbols. Note, from the given grammar, input symbol is A, C and D. That is terminals. Okay, what about the stack symbols? Stack symbols are the non-terminals in the grammar. That is S, A, B. Okay, what about Z0? I'll come to delta. Don't worry. Okay, what about Z0? Initial stack symbol. Remember, Z0 is initial stack symbol. Now, in this example, initial stack symbol will be S. Why? Because S is the start symbol. So, initial stack symbol here is always the start symbol of the given grammar. Okay. Now, finally, how do you find transfer function delta? Very interesting. Just see, to find delta, what we do is we take the first production. The first production given in the grammar is S derives AB. Now the delta gets constructed automatically as follows. We write delta, we are constructing the transfer function, and in which state the machine is. Now come on, there is only one state. Observe, in our machine there is only one state. So in state Q0 we say if the machine reads A and top of stack is S. You can remember this as only Q0 is the state, so nothing extraordinary about this. But the right hand side, remember, started with a terminal. That terminal is written here, and the left hand side obviously is a single non-terminal. That single non-terminal is written here. This becomes the configuration, and the result is that machine will stay in Q0. Come on again, there is only one state. Machine can't change the state. So if it was in Q0, it will stay in Q0, and the stack will now result in AB. Just observe this portion after AB. That is simply written here. What it means is that if your stack contains S on the top, S is on the top as it says, then this S is simply replaced. This S is replaced here by AB. How are you going to show AB? Yes, you are going to show B at the bottom and A at the top. Remember, this symbol written over here, A, is always the top. You are reading the stack from last in first out. So you should show AB as B at the bottom and A at the top. Okay. So coming to this generation of delta, these were the productions. S derives AAB, correct? A derives AA. Let me refer. A derives C and B derives D. A derives C and B derives D. Okay. How do you find delta? What I was talking about. Transition function. Delta for this production, the delta was if in Q0 state machine reads A and top is S, then the result is machine stays in Q0, but this S that is on the top is simply replaced with AB. Okay, let's take second production. The second production was A derives AA. Just take, I am taking this production. A derives AA. How will you write delta for this? In Q0 state, when the machine reads A and top is A, then machine stays in Q0. There is only one state. And what is written after this A, you observe? What is written after this A? Simply capital A. That is written over here. This becomes the second transition. Now let's elaborate third transition. What is the third production? A derives C. How will you define transition for this? Delta Q0. If in Q0 machine reads C and top is A, then machine stays in Q0 and listen, whatever is there after C, we were writing it here. But now there is nothing after C. Nothing means there is epsilon. This means A has been replaced, this top has been replaced with epsilon. This is the pop operation. We are replacing A with epsilon means what? We are removing A. Take the fourth production now. B derives D. Now this can be written as delta Q0. So in Q0 when machine reads D and top is B, then the result is machine stays in Q0 and whatever is there after D, we were writing it here, but there's nothing after D, so we'll write epsilon. Okay, so what are the transitions that we have got? Finally, let's write them properly. Okay, for the PDA that we are constructing, for the PDA, the transitions delta that we have got is, first one is delta Q0 AS becomes Q0 AB, the first one. Second one is delta Q0 AA, correct? This one becomes Q0 A. Third one, delta Q0 CA, small c A becomes Q0 epsilon. And fourth one is delta Q0 DB becomes Q0 epsilon. That's it. Once we have constructed delta, we have constructed PDA. Oh, what? How come? This is PDA. What I have written is PDA. We can only draw it in the form of a picture now. Tell me, only one state is there. Are you understanding? Q0 state. This is our PDA. This is initial state and this is the only state. How do you write this first transfer function? In Q0 when machine reads A and top is S. So you'll write A comma S. In Q0 state when machine reads A, top is S, then this S is replaced by AB. Check that this S is replaced by AB, but the machine stays in Q0. Second transition. In Q0 when machine reads A and top is A, then that A remains A. Just check, there is no change here. This A remains A. Third transition. In Q0 when machine reads C and top is A, then that A is replaced by epsilon. A is replaced by epsilon. This is pop operation. And the fourth one is in Q0 state when the machine reads D, top is B, then B is replaced with epsilon. There is no final state, just observe. What are the other details? I hope you remember. This is delta that I have written for our PDA. What are the other details? Q, set of states, only one state. Correct? Sigma, input symbol, all terminals, ACD. Right? Stack symbols, all non-terminals, SAB. Yes? Z0, initial stack symbol, S, start symbol. This will be there initially on the stack. Correct? And what about delta? That we have written here. And in fact, using delta, we have drawn this picture. What about F? Oh, come on, there is no final state. There is absolutely no final state. Correct? Done. We have constructed PDA. But wait a minute, what does it mean? I hope you will understand when I execute the PDA actually for some input. Okay, but give me some time. I will redraw the PDA here. Q0 in A comma S A B. A S A B and A A A A A A. Just bear with me. C A epsilon D B epsilon. C A epsilon and D B epsilon. Okay. This was the GNF given. Yes. Take some small string, rather smallest string generated by this GNF. Okay, you might have found out the smallest string generated by this GNF is ACD. Yeah, ACD, because S generates AAB, then A can generate C directly. Just see third production. A can generate C and B can generate D. So ACD is the smallest string. Now let's give ACD as the input to this PDA. Correct? So how are you going to show this? How are you going to show the working? Just check what we can do, is that we can write that the machine is in Q0 state and we have given the input ACD and the stack contains S initially. Oh, yes. The initial symbol on the stack is our start symbol, not Z0 this time. And wait, in Q0 state, machine is going to read A. Remember, PDA reads only one input symbol at a time. So although we have shown the entire input here, but PDA is going to read A. So what's the triplet we are having? Q0 is reading A in. From the input, Q0 is reading A and top of the stack is S. Yes, top is S. So do you have this triplet Q0 AS? Yes, of course. When Q0 reads A and top is S, this is the triplet. Then machine stays in Q0. Okay, machine will stay in Q0. But what will happen to this S? This S will be replaced by AB. Check it out. This will be replaced by AB. I hope you are understanding. S has been totally replaced by AB. That's how we read in this form of PDA. And the input remaining is CD now. Just watch, the input is now CD because this A has been already consumed from the input. Now Q0 is reading a C from the input and top is A. So how will you show it in our picture here? Stack was containing S initially, but now the stack is containing B, A. A is on the top. Correct? A is on the top. So do you have any such configuration? Q0 is reading C and top is A? Yes. Check this. Q0 is reading C, correct? And top is A. Top is A. Just check this configuration. Then what are we saying? That we stay in Q0, but this A has been replaced with epsilon. That means this A has to be removed and only B remains. That's pop operation. So what is the stack now? The stack contains only B. A has been removed and the input now contains only D. I hope you understand. Correct? Now Q0 is reading a D and top is B. Oh yes, we have that. We have that configuration. Q0 is reading a D and top is B. Then what's the action taken? Yes, that B has been popped and replaced with epsilon. We stay in Q0 and that B has been popped. That means there is nothing on the stack. Check that B also has been popped, then stack has become empty. I have shown that as epsilon. Now in all these previous steps, we could have shown that the string ends with nothing, epsilon. Here ends the string. So now nothing is remaining after consuming D. Nothing is remaining in the input. Input is over and stack is empty. So you may recall that we had a PDA of the form PDA by final state. This PDA had final state. And the second one was PDA by empty store. Empty store. This PDA that we have constructed does not have final state, but PDA will work on the basis of empty store. What does it mean? To accept a string, two conditions must be satisfied. One, input is finished. That means you have reached epsilon in the input. And second, the second qualification required is the condition that should be satisfied is stack should be empty. Stack should be empty. Both should be at the same time. Input must be over, just check, and stack must be empty, and both are satisfied. Then we say the string given ACD is a valid string and it is accepted by PDA. Why it is accepted? Come on, because it was valid string according to this grammar. Surely. Correct? Now let's take one more example. Let's very quickly dry run this PDA on the paper. You will agree that another string accepted by this grammar is AACD. Just check, AACD. Give me some time. So AACD is another string which is accepted by the grammar. So it should be accepted by the PDA because we have constructed PDA for the given grammar. Correct? So let's show the steps very fast. So AACD is the string. We are in Q0 and initially SCS, the top of the stack has to be S initially, the start symbol. Now Q0 is reading A, top is S. Just keep watching the transitions. Then we stay in Q0, input pending is ACD, but S is replaced by AB. So what we have is S gone and AB there on the stack. Now Q0 reading A, top is A. Then we keep that A as A. Just check this transition. Here Q0 is reading A and top is A, comma was pending, top is A, then A will be kept as A, no change to the stack, this is no change. Then Q0, CD remains in the input, correct? And the same stack AB, same, there is no change because A was kept as A. I hope you are understanding. Now Q0 is reading a C and top is A. We have this transition, Q0 reading C, top is A, and we will pop this A. So we have Q0, D remaining and B remaining. So this A has been popped. Now Q0 reads D and top is B. This transition we are going to use and we are going to pop B. So Q0, epsilon remaining, nothing remaining in the stack, and B is also popped. This B is also popped. Then input is finished and stack is empty. Both conditions are satisfied. Then this string AACD is valid. Yes, and it is accepted by this particular grammar. So how easy it is to construct a PDA given the GNF? Now I remember early in the lecture I told you that whenever you construct a PDA using GNF, then you get a non-deterministic PDA. Now it was a coincidence here that we have not got non-deterministic PDA. If you are not understanding this point, don't worry. We will take one more example in the next video. We will take some GNF and we'll very quickly construct PDA and then we'll say, oh good lord, this PDA is a NPDA. Okay, I hope you have understood all the points about how to construct PDA using GNF. Thank you very much.